plus 2 power 2 plus 2 power 1, which by binomial theorem is 2 power 5. Math works. You see what I'm saying? A complete Bayes network essentially says, I think everything is connected with everything. In which case, the worst you can do is you have to specify 32 numbers. The only question would be whether you prefer specifying conditional probability numbers or you specify joint distribution numbers. That's the only difference. In every other case, when certain things don't affect certain other things, if there are certain conditional independence assertions, right, then you would essentially basically wind up taking these conditional, you will wind up taking fewer numbers if you were to take conditional probability. And then you multiply them. You don't multiply, your computer multiplies. Let the computer do all the junk work. And it will get it to you to do perfectly. And in fact, your computer science part of your background will say, if I need to just answer a single query, I don't first generate the entire joint distribution. That was the whole point in logic. We didn't right away write the joint distribution. If you have 10,000 variables, we didn't write a 2 power 10,000 truth table. We also figured out this notion of proof theoretic inference, which can be, in the worst case, as bad as the model theoretic inference, but in the best case, it can be much, much better. That's what Bayes network inference does. Nobody actually converts this into this. But this is the only way you know that the theory holds. You understand what I'm saying? Just like we thought of in the case of resolution refutation, resolution theorem proving, etc. You try to prove that resolution as a rule is sound by going back to the truth tables. But that was the last time you looked at the truth tables. Proof theorem, when you're doing proofs, you just do refutation. That's what Bayes network inference is. Okay? So you pretty much know everything that's important to know about Bayes networks. This was actually from previous time numbers, but I just replaced the same thing. And then I want to make two things clear. One is, remember you saw this picture before? One time I just sort of showed it. Now you have a much better way of understanding this picture. Okay? In particular, this was the epistemological commitment, which is, what do you think the world is made of? Is it true, or truth and falsity, or somewhere in between? Okay? And then basically, this is the ontological commitment. And the probabilistic and the propositional logic, ontological commitment is basically what the world is made up of, and epistemological commitment is what is your knowledge state. And in the case of probabilistic reasoning, the knowledge state is degree of belief. In the case of propositional logic, it's basically, it is true or false. You should be able to say whether it's entailed or not entailed, that's it. And then in terms of what the world itself is made up of, it turns out both probabilistic logic and propositional logic make the same assumption about the world. They believe that the world is made up of single colored puppies. It's either black or white, either true or false. It's just that I have 15 words, I don't know how many fraction of the words is there a black puppy versus white. Fuzzy logic, on the other hand, basically says the world is made up of statements which can, in a single word, the statement can have a truth which is between 1 and 0. That's why this picture is useful. The other thing that I want to show, I don't know how to stop that. Maybe, let's see, let's see if I can do this. Yeah, I can do this, nice. This is the reason for that. Bayes networks and understanding this way of doing probabilistic reasoning is due to this great guy called William Pearl. Which is why our entire example was Pearl's home. And clearly, he got Turing Award. Okay, and you should watch him. There's an interesting ACM 50th anniversary panel on neural networks, deep learning, which he actually moderated, and it's hilarious because he's the kind of guy who first wants to know is there a theory before using it. Engineers basically want to use it and then hope for the best. Okay, so there's this one classic place where he looks at Fei-Fei Li and says, Fei-Fei, what do you teach in neural networks? How do you spend the whole semester? And you are thinking, of course, there's a lot to spend in neural semester. There are slides, there is the current filters, there's channel length. That's all bells and whistles, smoke and mirrors. In the end, the question is semantics. We don't have full semantics for many things. He is the guy who cared about semantics all his life. In fact, he also was the guy behind admissibility. He is also the guy behind, write this down. He has done great work on admissibility of heuristics. And he's also the guy who was behind game tree pathology. And basically said that the reason when you go deeper, you assume the backed up value is better. It's not because depth gives you more accuracy. It's because most reasonable games will have shallow traps. So when you go deeper, you're getting extra knowledge. Because you always do evaluation only if it's not a clear-cut win or loss. And the shallow trap is a clear-cut loss. Like, I mean, if you're playing chess where you've been checkmated and you basically the game is done, you still say, no, I can move this piece, I can move this piece. You shouldn't be playing chess. Right? So that's what he was saying. And so that's basically, he's the guy behind that. One last thing I want to actually ask you to think about, and this is here, which is, you guys think about this. What kind of world do you want to live in? We talked about this picture, right? You could have a world where this kind of a network is about the Berkeley earthquake alarm John-Carlos Medicals. Okay? You can live in a world where this network is true. You can live in the world that I only mentioned verbally, where there are basically, one of the guys will have 4 parents. The other will have 3 parents, the other will have 2 parents, etc. That's a completely connected case. Which world would you like to live in? You, the agent. If you are talking about using less brain power to think, because anytime you think your brain becomes hard and you die, okay. You say, let's just hope for this. And if it's not, we'll just still say that's the way it is. But if you believe this is the network you have, I would argue that you are living in a really sad world. There is nothing you can do to change anything. Everything is independent of everything. Your grade is independent of your homework problem values, independent of whether or not you show up to the class, is independent of everything else. You kind of probably believe this, in which case, what's the point in living? I understand you showing up to the class is not directly connected to your grade, but it's sort of kind of connected. If on the other hand, if your grade in this class depends on everything you do, the color of your shirt, whether or not you had a particular kind of cereal on whatever, September 14th, etc., every possible thing, then it's a really interesting word, but too interesting. Way too interesting. Everything can connect to anything. You'd rather not do any action. Here, you can act all you want, nothing changes. You see what I'm saying? In the other case, you are afraid of acting, lest bombs will go off. So really, you should be hoping for something like this, where certain kinds of independences will hold, others will not. One last thing, okay? We talked about ignorance and laziness. How did we capture them?
By not caring about
here is the question. So John might be calling for reasons other than alarm going off. Have you captured that? Have you captured that? Yeah, because he is loving. Right? And John won't definitely call just because alarm goes off. Because sometimes he might be taking shower. Sometimes he hates Pearl. Did you capture that? Okay? One last thing. So first of all, you understood something completely useful right now. Okay? You have basically realized that these probabilities do capture your ignorance and laziness. One last thing. Imagine I just give you these tables, everything is empty. The numbers are empty. Remember, if you're giving a Bayes network to some Bose expert and say put numbers, they're going to put numbers. And you'll tell them, just put numbers between 0 and 1. Do you think that the world goes kaboom if they put wrong kind of numbers? This is like a very, very mind-bending question. Here's my question. So, the experts may not know what they're talking about. The thing that you want to stop experts from doing is the computer crashes. Because it's basically leading to a mathematical inconsistency. So, my question is there a way, if all of these numbers are whited out, and you're just going to put numbers there, are there any constraints at all about these numbers, other than that they are between 0 and 1? Should these numbers add up to 1? If you realize this, you're already 90% ahead of people who think they understand Bayes networks. And if you realize that any damn numbers can be put there, and there won't be any kaboom, then you are like 99%. This is what happens when you're quote-unquote learning these numbers. Any damn numbers will be put there. And you are saying it's something is working, nothing went kaboom, so it must be right. Well, not ending the world is a very sad, low expectation goal to have. Thank you. We'll talk about it.